Hey everyone, welcome to my Calculus 2 series. In today's lesson, we're going to be talking about integration by parts. Firstly, let's start off by remembering the product rule that we learned in derivative calculus. So just to quickly remind you, the product rule would look as such. If we were to have the derivative of two functions that are being multiplied by each other, it's kind of being suggested in the product part. So like product rule corresponds to like the product of two functions, and if you remember, it's going to equal to f of x times g prime of x plus f prime of x times g of x. Essentially, we just take the derivative of the first one and then multiply it by the original second one, and then do the same process basically, but now inverting which one we take the derivative of. So this was product rule. Now the whole integration by parts kind of formula comes from this. If we were to take the integral of, let's say, this entire function, so we're going to apply it to all of this, right? And if we apply it to the left side, then we're going to need to apply it to the right side. So I'm going to go ahead right now and do that. So I've applied the integral to both sides of this little equation that we had here, and we can quickly see that these two are almost, well, not almost, they actually are opposites, because one is taking the derivative of it and then you're undoing it by taking the integral of it. So actually we can simplify this even further, and we just say that we're left with fx gx, and it's equal to the integral of this plus the integral of this. We're going to split this up. So now we have it, and one last thing that we're going to do is we're kind of going to rearrange this and solve for this. You'll see why later, and again, this is kind of leading up to the whole integration by parts. So we're going to solve for this real quick, and I'll show you why we did that. So there we go, we have arrived at this formula, and we can see that if we're taking the integral of a function and then some other function, again, let's remember that the derivative of a function is still a function. So if we're taking the derivative of, the integral of two separate functions, then we could evaluate it using this formula as long as we have the integral in this format right here. So here we are at integration by parts, and I'm going to show you how we can kind of make this formula a little more simpler, because as of now this looks a little much. So we're going to kind of simplify it, and I'll show you how we can do that. So the way we're going to start setting up this integration by parts is we're going to say that we have this function u, and then we have u's differential, and again, let's remember that the differential, so du over dx is equal to f prime of x, right? So let's remember this this is Leibniz derivative notation, and then if we want to solve for du, the differential of u, well, du would just equal to f prime of x times dx. So this is kind of the differential stuff. So again, let's not forget about this. So we're going to have u, we're going to have du, but we're also going to have v, and we're going to have dv. So this is how we're going to set up all of the integration by parts. Essentially, we're just going to have a function. The majority of the times we use u and v, so I'm going to be using them too. And then also corresponding to them, we have du and dv. So u for now we're going to let equal to f of x, and v we're going to let equal g of x. And then du, well, that's going to equal to, I kind of showed it, over here. This is just going to equal to f prime at x dx. And then dv is just going to equal to g prime at x dx. And again, why is this true? Well, if we want to take the derivative of this, we're going to get dv over dx is equal to g prime of x, and then again we can cross multiply this upward and get dv equals to this expression. So now that we kind of have these variables right here, what I'm going to do is I'm actually going to go ahead and substitute them into here, into this formula. Again, trying to make it a little more simpler, a little more readable. So that's going to look something like this. We're going to keep the integral, and we can see that, well, f of x is just equal to u, and then g prime x dx, well, that's equal to dv. It's equal to this. So we're going to have u dv here. And this is going to equal to fx times gx. Well, fx is u and gx is v. and we're going to subtract this from the integral of f prime times g, right? So this right here, it's kind of split up, but f prime dx is du, and then g, well, that's v, so we're going to have v du. So here's the simpler formula for the integration by parts. So essentially all integration by parts is we're taking the integral of two functions that are kind of separate from each other. Before, we only knew how to take the integral of like those functions that were in the table. Then we kind of saw the u substitution, or the substitution method, where if we would see the derivative of like an inner function, then we can use that method. But now this method is talking about if we have two functions that are completely separate of each other, like one isn't the derivative of another, and so on. So this is just the formula that we're going to be using, and I'm going to go through a series of examples kind of showing you how we can apply it, but these examples are also kind of going to be like edge cases, things to like look out for. So for this example, I'm going to go over both of the solutions. One using this simplified formula, and the other one using this kind of more expanded formula, if you like, but they're kind of the same. But just for this example, we'll go over both of them. Start off always by creating two functions, f of x and g of x. Actually, I'll call this g prime of x, and we'll see why. And then we're going to say that this is, well, f prime of x, and then this is going to be g of x. So if we look back at the formula right here, on the left side, we can see that we have the integral of f of x and then g prime of x, right? And that's kind of exactly what we have here, right? We can say, okay, well, this is f of x and then this is g prime of x. That's why I have these two first. So yeah, we're going to go ahead and say that this is just equal to x, and then this is equal to sine of x. I've added these two right here because we know we need them from the formula up here. We know we need f prime, and then we know we need g. So those are the only two computations left to do. So f prime of x, well, that's pretty simple. It's just 1. We take the derivative of f of x. And then g of x, well, to get from g prime to g, we need to take the integral. And the integral of sine x right here, well, that's just going to be minus cos x. So this will be minus cos of x. And now we have all the functions that we need. Simply all that's left to do is to plug in. So again, we're going to start off with this, which is the left side of the function. And it's going to be equal to, well, f of x times g of x. So let's go ahead and plug that in. Well, f of x is right here, it's just x, and g of x is minus cos x. So this is going to be minus x times cos x. And then what we're going to have here is we're going to have minus this integral right here, which is f prime times g. So again, f prime is right here, and g is right here. So we're going to have minus the integral of minus 1 times cos x dx. And I'm just going to bring this negative outside, so we're going to kind of simplify this by saying minus x times cos x plus the integral of cosine x dx. Now we can see how we've kind of broken up this integral from these two functions that were completely separate into a singular integral that we know how to evaluate now. So this is just going to equal to minus x cos x plus the integral of cos x, that's sine x, and then plus c. That's all that's left. Again, we're going to include the plus c because this is an indefinite interval. So that's solution number 1, where we kind of define these two functions. Again, if we want to use the simpler method, just by using u and v, I'm going to go over that too. The second solution is my kind of way of doing it. And the way I like to start them off is by saying, okay, we have u, and then we have du. And then I kind of invert it. So I say we have dv, and then we have v. And so u in this case is always going to be, we always want to choose u to be kind of the function that we can take the derivative of it and make it like simpler. So if we were to take sine x, the derivative of that would be just cos x. And cos x obviously isn't much simpler than if we were to compare it to, if we were to take x, right, the derivative of x would just be 1. So it would be a lot simpler. So we're going to take x, and then we're going to say that its differential, well, its differential is equal to 1 times dx. Again, let's not forget this dx here at the back. and dv is going to be this function right here. So this is going to be sine x, and then v is going to be the antiderivative of this, which is minus cos x. And so there we go. There we have kind of our setup done. What we're going to do is first, the way I like to remember is it's going to be this cross right here. So this is step number 1. And then this right here is going to be step number 2. And kind of helps me because step number 1, you simply slap them together. It's going to be u times a v. So it's going to be minus x cos x. And then we're going to subtract the integral of step number 2, which was du, slapping du and dv together, which is essentially just 1 times cos of x. Let's not forget this dx there. That's why it's important to keep them. Again, we can go on to simplify this, just say it's minus x cos x, and then we're going to say this is minus the integral of cos x dx. Then we can, again, simplify it to solve the actual integral. So there we go. We can see that we have arrived at the same answer using both methods, except personally, I prefer this method, so it's the one we're going to be working with. So now we have this integral of ln x, right? And we've seen that, okay, well, in order to kind of apply this integration by parts, we sort of need 2 functions, and this looks very weird. It wasn't in the chart. Actually, maybe you know it or not, but I'm going to show you how we can derive that answer using integration by parts. And again, there are sort of 2 functions here. There is kind of just a 1 there. Like ln x is the same thing as saying ln x times 1. So we just have a constant function there, and that function is y equals 1. So again, like usual, we're going to set it up by saying u and then du, and then inverting it, saying dv and v. If we have u set as 1, right, then this right here, the derivative of a constant function, is just going to be 0. So in a sense, it is simpler, but then with dv, we're going to be left with ln of x, right? And to get to find v, we sort of need to already take the integral of this. So it's kind of like, if we can do this step from converting dv into v, then there's no point of this integration by parts, because we're essentially just looking for the ln, or sorry, for the integral of the ln. So we don't really know how to go from dv to v. That's actually what we're doing in this question. So that's why in this question it would be appropriate to set u to be the ln of x, and then its derivative would be 1 over x, and then dv to be just 1, and v, or sorry, this would be 1 dx, and then this would be dx, and then v would just be x. And again, just to reiterate why we can't have dv right here being ln x, right? If we have dv is equal to ln of x dx, right? Well, then we can say that dv over dx is equal to ln of x, right? And now we're saying that, okay, well, the derivative of some function is ln x, right? What is the antiderivative? And that's what this, again, that's what this problem is about. So if we can solve for what v was, the original function was, then there's no need to evaluate this integral at all. If we kind of can make this jump from dv to v already, then we've already solved this problem. But again, we don't know how to do that. That's why we're solving this problem by integration by parts. We have the 4 things set up, and again, this is going to be step number 1, and this is going to be step number 2. So we're going to slap u and v together, and we're going to get that integral equals to u times v, and then it's going to be minus the integral of the second step, which is 1 over x times x dx. And we can see how this simplifies already. These x's will cross out. I'll mark it in green so we can see what we're talking about. These x's will cross out, and we're going to be left with x ln x minus the integral of 1 dx. This sometimes people just, actually the majority of the time people just write this instead of 1 dx because it looks a little cleaner. And now we have this integral to solve, and all that's going to be is just going to be x. So we have x ln x minus x plus c. So there we go. This is the integral of this function right here. Even though it looked like it was pretty simple and stuff, but the antiderivative is a little more complex. And I'm not 100% sure if it was in the table or not, but It is pretty common, so maybe you should memorize it, but I personally don't like memorizing stuff. I'd rather derive it. So there it is. Here's kind of how we derive the antiderivative of ln x. Okay, so now we're on the third example, and here is where things kind of start picking up. Again, these are kind of, all these examples are ways to practice integration by parts, but in each of the examples I'm showing something different. So this, again, now we'll see another technique to evaluating these. And we start off just like usual by labeling our function u, by labeling du, and then dv and v. So one of the more common problems that I see in integration by parts is people don't know which one to choose for u. And again, I mentioned that you should probably be choosing the function that is going to be simpler once we take the derivative of it, right? Once we evaluate for du, we want that function to be simpler than u was. Let's take a look at this example, right? If we take e to the t as u, the du, well, the differential of u in this case would just be et times dt, right? Like it would just be the same thing because the derivative of e to the x is just going to be e to the x. So in this case, it's useless taking e to the t as u because it's not going to simplify anything. But we can see that if we were to take t squared as our u right here, well then the du would be a little simpler. We would kind of knock off a power. It would be 2t, right? So now all of a sudden we've kind of lowered in complexity. We have t to the power of 1 instead of t squared. And this is how I'm going to choose to do this one. Now for dv, obviously we're going to choose the other function, e to the t. By the way, this should have a dt and this should have a dt. And then v, well, what's the antiderivative of e to the t? Well, it's simply just e to the t. So again, we've set up our 4 little variables, and now all that's left to do is apply step 1 and then apply step number 2. So first we're going to slap together u and v. So we're going to get t squared e to the t minus the integral of du times v. V is going to be e to the t, and then du is going to be times 2 to the t dt. And now we can see that before, the integral we were getting here was very simple, right? Yeah, in this example, it was just going to be the integral of 1. And then in this example right here, well, we were just getting the integral of cos x, which was also very simple and we knew how to solve it. But in this example, we can see that, again, we're getting 2 functions and they kind of had nothing to do with each other. So again, we need to apply integration by parts a second time. So now for the second time, we're only going to be solving for this integral right here. And then we kind of plug the result in. So let's solve for this integral by integration by parts. So again, we're going to set up our u and our du. We're going to set up our dv and v. And as we saw in the previous example, taking e to the t as u is almost useless. So we're going to take 2t as our u, and our du is going to be 2. And again, we see that we reduce complexity because now it's t to the power of 0. This is going to be e to the t, and then v is just going to be e to the t dt. So this integral is going to equal to 2t e to the t, and then we're going to subtract the integral of step number 2, which is going to be 2e to the t dt. Now if we do a little more simplifying, we can bring out this 2 outside of the integral, and we're just going to be left with e to the t dt. And now we know how to solve this integral. This is a function that we know how to solve, and it's just going to equal to this. The integral of e to the t is just e to the t. So here we have this integral solved. But we're not done yet. If you remember, this was part of the other integration by parts. So now we need to sub this into the other integral that was right here. So I'm going to continue over here, and we're going to be left with t squared e to the t minus whatever the result was for this integral. In this case, it was 2t e to the t minus 2e to the t plus c. Now if we go on to simplify this, and there we go, we have solved the initial integral, which was right here, by applying the integration by parts 2 times. So now for this last example, we'll see kind of one of the last edge cases. I'm sure there's a few more, but this is kind of a notable one. So we now are going to try to set up our 4 little variables that we have. All right, so now let's choose. If we take sine x to start as u, well, that doesn't really help us much because once we differentiate it, it becomes cos. But then if we take e to the x as our u, then that derivative is just going to be e to the x. So we kind of don't know which one to take. And in this case, I'm pretty sure it's okay to take either one of them as u, but I'm going to take e to the x as our u, and then this will be e to the x dx. The other one is obviously going to be sine x dx, and then its antiderivative is just going to be minus cos x. So again, we're going to apply step number 1 and step number 2. So now we've solved it and we've arrived at this integral right here. We can see that the functions again are, it's not a simple integral to solve yet, and the functions are kind of completely separate from each other. So before going on to solve this, first what I'm going to do is I'm going to move this negative out of the integral sign and just simplify it a little bit. Now we're going to be solving for this integral right here. So we're going to set it up the same way. We're going to have u du, dv, and v. And again, like in the first part, I'm going to select e to the x to be my u, and e to the x dx to be my du. Now this will be cos of x dx, and v will now be sine. So let's go ahead and solve our second integral right here. So it's going to be step number 1, and then step number 2. If we notice something, we have essentially come back to the original integral that we started off with. This was the original integral that we started off with. And we can see that we've come back right back to it. So if I kind of write everything out right now, this is what we have. So this is basically where we're at. This e to the x comes in from the first set of integration by parts that we did over here. This next part right here, all of this, well, this is from the second integration by parts that we did, which was over here. So we're basically at this equation, and it's pretty easy to see how we can solve it now, right? We're trying to solve for this integral, and we have it on both sides. All we got to do is bring this integral over to this side, and then we're going to get our answer. So we're going to have, if we bring it over, we're going to get 2 times the integral of e to the x sine x dx. This is going to equal to minus e to the x cos of x plus e to the x sine of x. But we weren't looking for 2 times that integral, we were just looking for the integral. So all we got to do to get rid of that 2 is divide it by 2, divide it by 2, and our final answer is going to look like this. There is our final answer. And again, this technique was a little different than the ones that we saw, but we just need to realize that we've come back to the same integral that we started off with. We just need to bring it over to the other side and kind of isolate for it, and that's it. So that concludes my first lesson for Calculus 2, and that concludes the lesson for integration by parts as well. Hopefully you enjoyed this video. If it's helped you out at all, please like and comment as to what it helped you out with. Like usual, if you're new to the channel, please like, comment, and subscribe. It's greatly appreciated. And yeah, I will catch you guys in another video.